So today, we're talking about AI and science, and physical science. We're talking about how AI goes into physics and chemistry. And I have some good videos for you guys today. So let's get started. So AI in physics and chemistry. So AI's application, let me actually. So AI's application in the physical sciences extends far beyond conventional data analysis. It has been pivotal in advancing research areas such as quantum mechanics, fluid dynamics, and astrophysics. For instance, AI models are utilized in quantum chemistry to predict molecular properties, reducing the need for expensive and time-consuming lab experiments. So, example one, let's say material discovery with AI. AI-powered models such as the ones developed by the Materials Project and DeepMind's AlphaFold predict material properties and protein structures, enabling faster discovery of novel materials, pharmaceutical compounds. These AI models analyze millions of possible combinations and identify those with the most promising characteristics. Example two is something like AI in astrophysics. In astrophysics, AI is used to detect exoplanets by analyzing data from the telescopes. One example is NASA's use of deep learning to identify exoplanets in the Kepler space telescope datasets. Traditional methods would take months to analyze this data, but AI algorithms can process it in a fraction of the time, even identifying subtle signs that indicate planetary bodies. So it's in this case, it would be like you know how they send signals outside to space and with satellites and big dishes. These signals they don't see like the exact stars, how they look or the galaxies, but it sends back these signals and images, which gets converted to images then. Like they don't see these stars because they're so far away, but machine learning helps them like interpret these frequencies into pictures. So we kind of see these stars and galaxies from afar. All right. So a little background, going into AI with physical science would be the spin glasses example and the statistical mechanics. All right. So the relationship between AI and physics is reciprocal. Many AI models are inspired by physical principles. The AI is also used to solve physical problems. Concepts like energy minimization in neural networks mirror the way energy states are minimized in physical systems like spin glasses. Example would be spin glasses in neural networks. Spin glasses are magnetic systems with disordered spin interactions, leading to a complex energy landscape with multiple minima. These analogies, analogs to how a networks optimize their weights by navigating through lost landscape, several local minima. Just finding a ground state in a spin glass is challenging. Finding the global minimum in neural networks that we talked about in their loss surface is fundamental. It's a fundamental problem in training AI models. Example two will be statistical mechanics and machine learning. Statistical mechanics provide insight into how the behavior of large-scale systems, which is useful in understanding neural network dynamics. Techniques like Monte Carlo simulations and the partition function are borrowed from physics to calculate the likelihood of different configurations, which is similar to how probability distributions use probabilistic machine learning models like Bayesian networks. These examples show how concepts of physics not only influence AI, but also helping in addressing the computational and optimization challenges inherent in large scale. Let me show you guys this here. So you can kind of take a look here at how statistical mechanics work. You know, like how atoms need energy to react, right? They need to have enough potential energy in them or enough energy to help them make these reactions, right? They don't have that energy in them. They don't make the reaction. That's why we use heat, right? to give these molecules energy so they can react, right? So it kind of goes into that, especially into the spin glass model. Like you guys see how like randomly how the electrons and ions here are randomly taking directions, and how it has like this frustrated configuration where the ions are working against each other. Same thing that happens inside neural networks. So this is kind of how it, this figure right here kind of shows the spin glass magnetism and how it works into machine learning. It's the same concept. You see how like they're bounding back and forth on each other. It's like it shows you kind of like that frustration configuration. And this is kind of like the equation that goes into it, the mathematical equation. It's statistical mechanics, Bayesian probabilities, and machine learning. This is what the equations look like. It's a little bit of a complex concept, but you know, just to show you guys, it's not like I'm not gonna go real deep into it. I'll show you a video right now. It kind of shows this concept a little deeper. This. See, it didn't align with it. Kind of shows that kind of concept. This is kind of like how the electrons on ions. Show like ions and electrons. Just to give you guys a perception and intuition, right? Like how these concepts roll into AI, right? Physics. AI and physics, areas of application. We talked about data analysis, modeling, and modeling analysis. So physics. Physics has been one of the primary beneficiaries of AI. especially in areas that involve large-scale data or complex systems. The three main areas where AI has made a significant impact are data analysis, modeling, and simulation. Example one would be particle physics and the Large Hadron Collider. The Large Hadron Collider at CERN, which is this project going on in Switzerland, I think, for Europe. It's like a big proton electron collider. Generates petabytes of data, which is a petabyte is like 1,000,000 gigabytes. Okay? It's 1,000 terabytes, so it's like 1,000,000 gigabytes. It's a lot of data. It generates petabytes of data from particle collision, like these little particles that we don't see with our eyes colliding with each other. AI is used to sift through the vast amount of data to identify patterns that might indicate new particles or confirm theories like the Higgs boson. AI's ability to detect these rare events with high accuracy is vital for advancing particle physics research. So in the CERN thing, like you can look it up online, CERN. It's like this big round thing where I think protons and nucleuses collide, and then they gather all this data, which is a lot of data because like on this small scale, a lot of stuff is happening at high speeds. So it brings back a lot of data to them. Example two would be gravitational wave detection. AI plays a crucial role in detecting gravitational waves by analyzing signals from LIGO, laser interferometer gravitational wave observatories. These signals are often faint and buried in noise. Deep learning models are trained to distinguish between actual gravitational wave signals and the background noise, which might be caused by outliers or extreme values like we talked about, right? Outliers and extreme values. Allowing the real-time detection of cosmic events like black holes, mergers. So, like, you know how far these black holes would be, how black holes in the galaxy are? There are like big vacuums cleaning up the galaxy from exploding stars and planets and stuff. It kind of goes like that. They bring in these frequencies, like I said, and then they analyze them to see all these pictures and figures from space. Example three would be quantum physics simulations. In quantum physics, which I think Jessica will be talking to you guys about in the last lecture. She'll be giving the last lecture and she'll talk about this. AI is employed to simulate quantum systems, which are computationally prohibitive using classical methods due to exceptional increase in required resources with system size. For example, Google's TensorFlow quantum library enables researchers to build quantum machine learning models and simulate quantum circuits, facilitating research in quantum computing. So quantum computing is basically the next generation of computing, right? They're making computers on an atomic scale in computation, which is going to make everything faster and more accelerated. Talking about modeling and simulation here. So in data analysis, like we said, we can do a lot of stuff. It helped out, create all these data analysis methodologies. So here's like a budget overview, something like this. I showed you guys some data analysis and charts, right? Campaign duration gives you a pie chart to see percentages, percentage distributions, time-based metrics like this. So regular data analysis, basically. And modeling and simulation. AI now can model and simulate the atoms and molecules like this. See, these are molecules and atoms right here. So AI now can take these proteins and DNA and model them into these shapes where you can see them from a closer look, you know what I mean? So this might be like a hydrogen atom, carbon atom. You guys took organic chemistry at all here? Not at all yet? It's basically chemistry that has to do with carbon, connecting with, it has 4 empty spaces. So this might be like a carbon atom, hydrogen atom, oxygen atom. So this is like how they model them right now. This is kind of like how DNA looks like. See how it's so clustered? So they kind of, this is how they see these things through AI programs, right? You know, these AI programs can let you structure proteins and DNA and all kinds of complex compounds into these figures where you can see like what molecules and atoms are going into it. It looks something like this in the simulations. So AI and physics simulation, it's like doing graphical stuff and game-like interaction and stuff like in games, like in video games and graphics, all these kind of graphics. Let me say. Simulations in physics often require solving differential equations or using iterative methods, both of which can be computationally expensive. Talked about that. AI models, especially neural networks, are increasingly being used to approximate these solutions, making simulations more efficient and accessible. Example would be fluid dynamics. You guys didn't study fluid dynamics. You'll study them in college. It's just the math of how fluids and air flow through things, right? Computational fluid dynamics simulations are used to study complex flows, such as aerodynamics around a vehicle, or the behavior of blood flow in the human body. Traditional CFD simulations require solving the Navier-Stokes equations repeatedly, which is computationally intense. Of course, AI can be trained to predict fluid flow directly, reducing the computational load by orders of magnitude. A notable example is NVIDIA's Fourier neural operator, which approximates solutions for fluid dynamics problems significantly faster than traditional solvers. So it can basically predict the motion of a fluid through a certain space or certain tight spaces or something like that. You know what I mean? It can predict that out of because it's very complex. Another example would be cosmological simulations. In cosmology, AI helps simulate the evolution of the universe. One model developed by a researcher at Harvard and MIT called Deep Density Displacement Model uses AI to predict the distribution of dark matter in the universe. The model can generate simulations that match observations of large-scale structures of the universe, providing insights into how galaxies and other cosmic structures form and evolve. Like I said before, they send these frequencies out, they get frequencies back. They use these neural networks to kind of interpret them and give you these figures where you can study further. That's in the space discovery. Here's a video to show how physical simulations can be done with AI. Show you guys this video. How detailed the simulation is, the wiggles. So the ground truth can be like a video taken from somewhere, and then the AI learns it. See, it's a very complex convolutional neural network. Talked about how convolutional neural networks do videos and images. This is like kind of the real video, and it can simulate it exact. It's crazy, right? system. This it may seem to you like a simple thing. No, it actually needs to get the simulation accurate. So these are different models that have been trained on this simulation. See this? All the movement is specific. Program like this, you can train all your tensors without even using any code, right? These thing, I wish I had this back then. So you guys seen how these very complex, like physical simulations, how the AI can learn these now and make its own simulations. It's since you guys know the complexity now, like we're in week 4 now, you have a good idea of how these networks are working and how complex they are. So picking up these very complex movements and like you saw that little sponge dragging down with all these hairs and everything, it has to pick up all these ranges of movement, like and it's amazing. It's very amazing. So to end the physics part, I'm going to show you another video on physics and generative AI. The generative AI in physics and robotics, generative AI models such as GANs, we talked about them, the generative adversarial networks. Adversarial because the generator and the discriminator are working against each other in there. And variational autoencoders like VAEs have the ability to create new data samples, predict outcomes, and even generate novel design in physics and robotics. Example would be GANs for fluid dynamics. GANs have been used to generate synthetic data sets for fluid dynamics, which can be used to train our other models or improve simulations. By generating realistic fluid flow patterns, GANs help simulate scenarios that are too costly to reproduce in physical experiments. So instead of having a room like this and having to fill it with equipment and having to do this and having to do that and spend all that money and all that time, we can have a computer do it for us, right? It's awesome. Another example would be generative AI in robotics. In robotics, generative AI is used to simulate sensor data or even entire environments. This enables the development of robots that can learn and adapt to new environments through simulation before being deployed in the real world. For example, OpenAI has reinforcement learning models, train robotic agents in simulated environments that are then transferred to the real world robots. So they teach, it's just like the self-driving mechanism. They teach the robots to see things and identify what they are, pick them up, don't pick them up, do all these complex things. So I'm going to show you guys another video here of how generative AI works in physics. We're teaching it from a simulator. You don't have to have the actual real environment. See this? Like it's a the omniverse is a simulation. It's a simulated environment where we're not going to put the robot, into the environment right away and let it learn from it. No, they have these multi-large language models in the simulators where it can create an environment for it to learn from. We're actually putting it into the real world, right? Awesome. So this was the physics part. Let's move on to chemistry. Generative AI in chemistry. Okay. All right. So The history and background, representations, machine learning, and science. First, chemistry is another domain where AI is making transformative contributions, from understanding molecular structures to predicting chemical reactions and discovering new drugs. Representing molecules and chemical reactions in a way that AI models can process is crucial for effective applications. Example, the Dendral project. One of the earliest applications of AI in chemistry was the Dendral project in the 60s, which used rule-based systems to infer chemical structures from mass spectrometry. You know, you guys see the spectrometer? How it picks up light waves of the atoms and knows you what atom it is and stuff. From spectrometry data, this system helped chemists determine the structures of unknown molecules, automating a process that would otherwise take weeks, right? So they did it all in a simulated modeling environment instead of going into the lab and doing all the mixtures and this and that and adding compounds. No, the computer did it. AI did it for you already, the machine learning algorithm or the model that was trained. Another example would be graph neural networks, GNNs, chemistry. Modern AI applications use graph-based representations of molecules that I showed you guys in the first slide, where atoms are nodes and bonds are edges. GNNs are a type of deep learning model. It can learn from these graph structures to predict properties like solubility, reactivity, and toxicity. For example, the model ChemProp uses a GNN architecture to predict various molecular properties with state-of-the-art accuracy. By using advanced AI models that understand the complex interactions within molecules, researchers can accelerate the development of new materials and drugs. What are some benefits and problems of using 3D structures of a molecule as input to an ML model? Think about what information you need to describe certain chemical relationships. Benefit would be distance between all atoms. You want to know the distance between the atoms, interference and shielding of electron-proton interactions, and more accurately describe problem 3D space. Take some image graph described with 3D Cartesian coordinates to get it into this kind of 3D look that I showed you guys, right? But in early studies, 3D matrix is data intensive. Visuals cannot be that accurate, but now they're very accurate because we have all the hardware and everything. If you guys want to know more about this, you can call Dr. Freeze. She got her doctorate into this, studying this problem. So you guys can, shoot her an email or call her. Want to learn more about it. It's like here, So we know that they have like models for the atom. You guys see these, I don't know, does this thing move? See how it there can be like 3 compounds with the same structure like this. Carbon, iodine, oxygen, this, it can be the same exact structure, but when you draw it, it's not the same structure. So that's what it can have the same, a totally different effect and a totally different everything, even though they have the same structure, number of molecules, number of nitrogen and everything. But in organic chemistry, you guys are going to learn that if the structure changes a little bit, like this NH2 goes from this part to this part, it can totally change the molecules' interactions, its effects, its everything, right? Also showing here the model of the atom as it, evolved through the years. Solid sphere in the 1800s, the plum pudding by Thomson, the nuclear model by Rutherford, how he made the nucleus. But now our quantum model is the one used now. Shows you this electron cloud and these little, pebbles, this is what's mostly used in modeling and simulations right now. Because it makes the most sense. And scientists can derive conclusions better from it. All right. All right. AI's role in chemistry encompasses elucidation, which is understanding molecular structures, predictions, forecasting chemical properties and reactions, and design, creating new molecules and compounds. Like I said before, we have this AI program that can, give you all these molecules made for you already and structures out of other structures without having to go like through all of this in a lab, right? You can do all of this through a machine learning. Example one would be reaction prediction. AI models like IBM's RxN for chemistry uses deep learning to predict the outcome of chemical reactions. These models can suggest reaction pathways, optimizing conditions for synthesis, even recommend regions to maximize yield. This application is particularly useful in synthetic chemistry, where you have to synthesize molecules in labs, where choosing the right reaction conditions can make or break an experiment. Like, I can make all these conditions in a simulation instead of, going to a lab and blowing up something, right? You know how scientists put stuff together and then it blows up and stuff. Yeah, like instead of doing that, you can just do it all in a simulator. The simulator is going to show you how everything works and reacts with each other. Example two would be drug discovery. We're going to talk more about drug discovery and AI for medicine on Thursday. And I'm going to do the breast cancer data set to show you guys some examples on it. AI models are transforming drug discovery by predicting the activity of compounds against various targets, reducing the need for expensive and lengthy lab tests. Like I said, you don't need all these expensive and lengthy lab tests. You have it simulated. Atom-wise and AtomNet, for example, use a convolutional neural network to predict the binding affinity of molecules, helping to identify potential drug candidates faster. So they want to see if this drug will work better or this drug will work better. They can do AI has streamlined various stages of chemical research from basic understanding to practical application in fields like pharmaceuticals. All right, take a look here. You guys can see how AI transformed drug discovery from this. Accelerated drug development, more effective drugs, improved clinical trial design, prediction of drugs by bioactivity. You know how the drug is going to interact in the body before testing it on mice or turtles or animals or whatever, you can do that in a simulated environment. Quality assurance, drug repurposing, drug combination analysis, how to combine two drugs, interactions, all of that you can do through AI in a simulated manner. Alrighty. So AI in chemistry simulation. We talked about drug discovery and how it's GPU powered. AI can reduce the computational cost, which is always a problem we talked about, of simulating chemical reactions, which often requires solving complex equations for using quantum mechanical methods. By learning from existing data, AI models can predict the outcomes of simulations with high accuracy. Example is the AlphaFold, or protein folding. One groundbreaking application of AI in chemical simulations is DeepMind's AlphaFold, which predicts 3D structures, like I told you guys, 3D structures of proteins from their amino acid sequences. Protein folding is a notoriously difficult problem because the number of possible configurations grows exponentially with the length of protein chain. AlphaFold has achieved near experimental accuracy in many cases, greatly accelerating research in structural biology and drug design. So instead of going in and, you don't know, it can have a million combinations in one molecule, right? So instead we can use something like AlphaFold, which, is going to show us all this instead of doing it in an experiment in a lab and probably blowing up something. You never know. Another example would be AI in molecular dynamics. AI models like, SeshNet are used to approximate potential energy surfaces for molecules, which are then used to simulate their behavior over time. This allows researchers to study phenomena like reaction kinetics and thermodynamic properties without resorting to computationally expensive quantum mechanics methods, which are all experimental and expensive. By providing accurate predictions at a fraction of the computational cost, AI is making it possible to simulate the study of chemical processes that were previously inaccessible. And let's take a look at this video. See, NVIDIA, they're on top of their game with AI. Otherwise, you would have to sit down and make all these calculations on your hand, right? You guys take stoichiometry, which is math chemistry, equilibrium, chemical equilibrium. You'll take that in college, I think, or maybe senior year. But instead of doing all these like on hand or another, slower software that doesn't have AI capabilities, AI does this all for you. So if you guys are like going to get into research or pharmaceuticals or any of these things, any of these fields, this stuff can be really, really good for beneficial for you. So we talked about generative AI in physics. Now we're going to see generative AI in chemistry. Chemistry generative AI models are at the forefront of molecule design and synthesis planning, revolutionizing how new compounds are created. Example would be generative models for drug design, models like Gentral, generative tensorial reinforcement learning, can design new drugs like molecules with specific properties by training on known drug structures and using reinforcement learning, can generate entirely new molecules that are likely to bond into a given target, accelerating the drug discovery process. So here we're talking about training it on known drugs that were made already and their properties. So it can make newer drugs and newer properties. It can make all these predictions. Another example would be generative AI for material design. Generative models are also used to design new materials with desired properties, such as superconductors or catalysts. You guys know how catalysts are used to speed up a reaction? Take this in chemistry. Put silver or like molybdenum or something like that into a reaction to make it react faster. That's what a catalyst is. For instance, researchers at MIT have used GANs to create hypothetical materials with specific band gap properties, which is essential for designing new semiconductors and photovoltaic materials to make like better solar panels using photovoltaic materials. Generative AI thus not only helps in discovering new chemical entities, but also proposes pathways for their synthesis, reducing the gap between theoretical design and experimental realization. Let's take a look at this video. gonna take forever, but you could do that. Amazing, right? All this software they made right now is like you have to go through tens of thousands of molecule structures. No, the computer can do it all for you. AI. Otherwise, they would have like had to sit down and go through all these structures and make all their calculations and then go back and do it again. And it's revolutionizing this field too. All right, so this is the last video, I promise, and last slide. And then I'm going to show you guys a regression model. I showed you a classification model last week, right? I'm going to show you a regression model today to show you guys how it's going to predict house prices based on certain features. So this is our last slide here. AI for science web application examples. It's user-friendly interfaces, domain library selections, modular Python programming. So this is gonna show you how data scientists do their stuff in all in one place, like mapped all in one place using Python and cloud structures. Web applications and cloud-based platforms have democratized access to AI, enabling researchers without extensive programming experience, so you don't have to have like all this deep programming experience, to leverage machine learning models for their scientific investigations. An example would be Google's Colab and DeepChem. Google's Colab provides a Google cloud-based environment for running Python code and machine learning models. DeepChem is an open source tool that integrates with Colab, allowing chemists and biologists to train AI models for molecular property predictions, synthesis planning, and more. This has opened up opportunities for scientists who may not have resources to they don't have the lab and resources, but they can use this program, right? Or expertise to build their own AI models from scratch. So we're going to take a look at Cosmotech, which is a cloud-based platform where all scientists come together, put their ideas, and everything is connected and mapped in an organized manner. Last video here. everything in one place. So you guys can kind of see how this whole simulation environment is, everything is in there for you in one like package, right? Where you can go like, if you want to change the parameters on one thing, you just go to that one node, click it, change the parameters a little bit, its relationship to another node. It's amazing, right? Everything, like if the employees doing all this together and scientists, it's all in one environment and they can all like collaborate. And it's all AI powered. Awesome. So this comes to an end of the lecture. And now I'll show you guys the last part of the lecture, which is I'm going to train a regression model on this real estate data right here. An Excel file right here. Let me first, yes. So this data set right here, we have 1, 2. So I have 1, 2, 3, 4, 5, 6 features. And the output would be houses price per unit area, which per unit area, I guess, would be like per feet area or something like that. In that specific area you're buying the house in or trying to predict the price. So we're going to be taking in transaction date, the data transaction, which is not that important of a feature, but I did, keep it. It might have been important. Then the house's age. We have like 32 years, 19.5 years, 34 years. Some houses might be like 7 years or something. Here. Third feature would be its distance to the nearest MRT station or transportation station. This is in miles, 84 miles, 306 miles, 506 miles. So this is another feature going in. It's distance from a certain transportation station. Next feature would be X4. It would be number of convenience stores. So here I have, this one has like 10 convenience stores around it. This one has 9, some have 7, some have 8, and it goes on. And it's latitude and longitude. It's exact position on the map, basically. So we have like latitude at 224.98, whatever here, and then, an X6 longitude, 121 something. So we have 6 features going in. On our output, which is Y, is going to be the price per unit area, which I think is per feet here, per feet, square feet, price per square feet. So what I'm gonna do first is I'm gonna load it into Jupyter Lab here. Go to first. Desktop, real estate. Okay, it's uploaded. It's in my Jupyter Lab. So we're going to start another Python notebook here. And I have it here, prompt engineered. And I'm going to show you guys the prompt I engineered here. So we can add the code in. First, I told it what? The CSV file, real estate, has the columns as follows, with one value for each column for clarification. So I gave it all the columns in. So it's told it that number has the number of the house. X1 is our first input feature, which is the transaction date. X2 is our second input feature, which is the house's age. X3 is our third input feature, which is its distance to the nearest transportation station. X4 is our fourth input feature, which is the number of convenience stores around it, like Target, Walmart, whatever is around it. X5 would be its latitude, exact position on map. X3 is longitude, also position on map. And Y is our output feature, which is the house of unit area, which is per feet squared, square feet. So I'm telling you here, create a linear regression model that will predict house prices based on these input features, which I showed all 6 of them. And the target output feature is Y, which is house price of unit area. So build a regression model, check for accuracy with training and testing data, use 5 different inputs to test the model's performance. So first of all, what we're going to do is extract the file and see the first 5 rows using this piece of code here. Oh yeah, I'm gonna libraries in first. First, I'm going to import all the libraries we're going to be using. Okay, I ran that cell. So here we're importing the linear regression from sklearn here. And we're going to use linear regression. Then we're going to load the file to get an idea. So use the head function here on the data frame to see our first 5 rows. You get an idea what's in there. The transaction date, house age, distance of nearest station, number of convenience stores around it, latitude, longitude, and Y is our target. These are actual ground truth. So it's labeled data because we have actual ground truth here. And then first, I'm going to check if there's any missing values and see if we have any missing values, like we said before, which I'm pretty sure we don't. See print data frame dot is null. See what is null here and see the sum of all the nulls. All right, 0, 0, 0, 0. We don't have any missing values in any of the columns, which is good. So we can start training our model. First thing is we're going to split the model into testing and training data, like we said before. We don't have to split into validation data also because it's not that complex of an issue. So it's just show you guys, we don't need validation set. So we're just gonna go with a training and training test set. So here I put test set size will be 0.2, which is 20%. And the other 80% are going to be used for training, which is, I guess, good. You know, most engineers go for that. Random state, they always put 42 here, which is most machine learning engineers do. Then train the model. First, create the model using the linear regression function we imported up there, which is linear regression here. We're going to train it's going to be stored in this model. And then model.fit, we're going to put the X train and Y train from our split here, using only a train data. So we're going to take X train and Y train from here. We're going to fit the training data into the model, run it. Here we go, trained already. Then I'm actually going to I'm going to use the evaluation metrics to see how the model did first. this here. So up here, I imported what? I imported mean absolute error, mean squared error, and R2 score. These are the three metrics to evaluate a regression model, right? The lesser they are, the better the model did. Last week, we did a classification model, and it had three other classification models. You evaluate them using accuracy, precision, and recall. These are the ones we used last week. And the higher these ones are, the better the model is. So in this regression model, we're using three other mean absolute error, which is MAE, mean squared error, which is MSE, and R2 score. These need to be a little like, we're gonna see now how good the model did first. Numbers. Oh, this is not, one is not doing that good because, you know, we have mean squared error here is a little high. Mean absolute error is, yeah, it's fine. And this is with the training data, this is with the testing data. But the testing data is doing good. It's weird actually, because the testing data is supposed to be doing worse than that, but I think it's because a little bit of a noisy data set. I don't have time to go that like back and do all the corrections and everything, but just to show you guys an example. So these are the three metrics used to it actually included also root mean squared error. So the lesser these are and closer they are to zero, the better your model did. But with classification, when we're talking precision, accuracy, and recall, the higher these numbers are and closer to one, the better the model did. So this model, it's not doing that good or not doing that bad, but you know, still, you know, something, it's good. So we did that. I'm gonna test it on 5 different inputs. Okay. So I have these 5 different inputs here. And we're gonna see what prediction it's gonna make on these 5 inputs. So first input, I have the transaction date as 2012-9/17, which would be September 17th, 2012. Its age is 19.5 years. Its distance from the station is 306 miles. It's got 10 convenience stores around. Its longitude and latitude on the map are 24 and 121 and fractions. Our second input would be this. Third input would be this. So we'll see how it does with 5 different inputs. All right, so predicted the first one at 49.34 something for the unit area price. Second input it predicted as 49. Third it predicted it at 37. Fourth one it predicted at 75. And this one it predicted at -4, which is weird. But this is to show you guys how regression works, right? I showed you how classification works. The output is going to be a category, which is cat or dog, malignant or benign, yes or no. That's for classification, right? Last week we did 3 kinds of flowers. We classified Virginica, versicolor, and what was it called? The other Setosa. So this one is predicting numbers. It can be continuous numbers. It doesn't have a certain class. It's continuous numbers. This is a regression model, right? So we have 5 different, you know, predictions here, which is good, you know, model's not doing that bad. But from these numbers, it doesn't show it's that good because of the data here is a little dirty. Needs a little bit of adjustment or something to make the model run a little better. And then I want to graph actual versus predicted to take a look at how the model did. How well it did also, to see it from a graphical visualization point of view. So we're gonna do actual versus predicted. I think this one was. Here it is. Here. See how it's scattered up here? So it did well. You know, the points on the line are where the actual and the predicted were actually accurate. But here it might have like, it been actual was 10 the price was 10, but it predicted it as something else. So, you know, it's not that good of a model because we have a lot of error. Remember, I told you guys the cost function, how it has to be, you know, closer to the line here. So we have some error here, but we have some good points around here for the prediction. But since these evaluation metrics are not that good, because probably there's, you know, we need to go back and do a lot of adjustment on the data. I would say it's a good model, not that bad. And that's it, you know. This is a simple regression model. Using, you know, we took a look here. We assigned our input as transaction date, house age, distance to a station, number of convenience stores around, its latitude and longitude, and our output would be the price of the house. Trained it, made some good predictions here. Don't know how accurate they are, but you know, it's just to show you guys how regression works, basically. So on Thursday, I'll show you guys the breast cancer data set, which has 30 features. It has 30 input features, and a lot of things like how concave the cancer is, how the viscosity, how sticky it is, how, you know, protruded it is. All these features are going to go in to give like if it's a malignant or a benign cancer. And I'm going to show you this on Thursday's lecture, which is AI in medicine. So this wraps up today's lecture, guys, and I hope you liked it. And I'll see you guys on Thursday.
Thank you.
No problem.